let's get started though. It's 7:04. I'm sure we'll have some people hopping on late. Did you hit the recording? Okay, we're recording.
I did. Be all set.
All right.
Hello.
So, hey everyone that's dialed in. We have, I know this will be viewed by a bunch of people later, which is why we're recording it. FTS now has something like 300 or so odd members that are all over the place. And we just had our Boston winter meetup. And so we want to spread the love a little bit and get you guys some remote tech talks for all the people that aren't in Boston. This is just like a fun thing that we've been doing. We've had a couple others that are on the YouTube channel, so this one will be posted there as well. And I'm going to intro Mikhail. So Mikhail, aka Bear Loga, aka Papa Dank, is a data analyst at the Wikimedia Foundation. It's the nonprofit organization behind Wikipedia. Before that, he was involved in research focused on Alzheimer's disease and HIV-associated neurocognitive disorders. His formal training is in mathematical statistics, but he enjoys all aspects of data science as a jack of all trades. He loves baking, cooking, brewing coffee, making people laugh, and playing games, which is what we were just nerding out about a minute ago. And he lives happily in Pennsylvania with his wonderful wife and pets. So with that, Mikhail, thank you so much again for doing this, by the way. Let you take it away. And he has been kind enough to offer interactive just questions throughout the session, so you don't have to wait till the end. Please just type it in the chat, and he's going to have that up. And if he thinks it's a good time to do so, he'll answer your questions. So go ahead.
Yeah. Hi. So I will say that if you post a question, if I think that I can totally fit into the the current point, then I will do so, and otherwise I will wait until the end to address it. All right. So I will talk about my workflow for Bayesian modeling and reporting in R. If you go to if you open up the event information, you can actually open up the slide deck on your browser and follow along if you want to, but I'll also go through it here. And if you go to that GitHub URL, then you'll be able to check out like a bunch of source code and whatnot. Okay, so what this talk isn't, it's not a lesson in Bayesian statistics. Also, although I will be like covering that just a little bit, like as a refresher. If you have the slide deck open, then you can go to any of those links to learn more about doing Bayesian modeling. That's not my goal here. If you're a hardcore frequentist, my goal isn't to make a Bayesian out of you. That's for other people to do. This is just me talking about a workflow that was pretty successful for me, and some tips for like how to use TidyVerse, how to present results in a really nice and pretty way. But okay, let's just dive into a quick refresher. So Bayesian modeling is about modeling the data generation process, and the way you do that is you specify what the likelihood of the data is, and you provide some priors. So you say like you specify prior probability distributions for your different parameters, and then the likelihood and the prior and the data, they come together, and through the wonderful Bayes theorem, it creates this beautiful baby called the posterior distribution for your parameters, given the observed data. And what's really cool about Bayesian modeling is you really make like all of your assumptions explicit by specifying these various probability distributions and these probabilistic relationships between the parameters and how they all come together. So let's assume that like this is where we're at, and let's keep going. So the R packages that I'll be covering, I'll be going through some of the TidyVerse packages. So this is a set of R packages that facilitate working with data. These include dplyr, tidyr, purr, and broom. I used rstan for modeling. rstan is an interface in R for using the Stan probabilistic programming language, which I'll get into later. I used the bridge sampling package for doing model comparison. And what's really cool is that it works with models that have been fit in rstan. I use Cable Extra for table formatting, and then R Markdown for the final output. This whole slide deck was also created in R Markdown, and also a package called Jaringen. So at the end of the slide deck, you'll see links to both of those. Suggestions. Okay, so if you go to the GitHub repository that has this slide deck, there will be an example report. That example report uses a R Markdown template that I put together for use at the Wikimedia Foundation for my team, and that is based on the Memoir template, which is this R Markdown template that's highly customizable, and it's really cool. And so if you want to see like how you might use it yourself to create like a report template based on that, you can check out the WMF PAR package, which I built using the Memoir template. And then I recommend TinyText for managing your LaTeX installation. It makes it much easier and simpler than like using MacTeX or other LaTeX management like solutions. Okay, so first, quick intro to TidyVerse. Also, again, I'll remind people if you have a question you want to ask, feel free to ask it in the chat. Okay, so the key component of the TidyVerse, I think, is the pipe. And when you look at code that includes the pipe operator, the way that I read it is like then do. So you do this and then do that and then apply this function and then do this other thing to your data. Tibbles. Okay, let me sell y'all on Tibbles. Tibbles are super cool, and the reason they're cool is if you've ever wanted to have a data frame in R where an individual like cell in that data frame had was an object, like a list or a complex like model object, Tibbles are what lets you do that basically. And when you have a data frame with like model objects or just like these complex objects, inside these columns, then you can use purr and other packages like dplyr and tidyr to work on those like complicated columns, basically. So I'll give an example. You know what? That is a great question for the TidyVerse advocate that is in the FTS. That's a great question for Mara.
I'll unmute myself, but yeah, I asked a question about Tibbles. So I'm, first of all, I'm like an old soul. I'm not gonna like hijack your talk or anything, but real quick, I get so frustrated sometimes with Tibbles because I use so many different packages that just break because they're used to a data frame and there's some weird thing about a Tibble. So yeah, we'll put Mara on the hook for answering that after.
Yes. The thing that I'll say, so like older packages that rely on data frames. Like I've had stuff break too because I was passing a Tibble or I think like in the early days of TidyVerse it was maybe it was called something else. But yeah, like one big problem is having to run like then as data frame, like as dot data dot frame,
Yeah,
Um, be, be,
I do
be,
that all the time. Like I'm literally like an old stick in the mud. It took me a while to go from base R to like dplyr. So don't judge. Okay, go ahead. Floor's all yours again.
um, but you can also have like data frames inside data frames, and then you can use per to operate them in a functional way. And then there's Broom. So Broom, uh, it you tidy models up with Broom, and it allows you to go from a model object into a tidy data frame that you can then use with like ggplot2 or cable. If you want to output like a markdown table of like parameter summaries and confidence intervals and whatnot. So here's an example. Okay. In general, I don't recommend using like I don't recommend like attaching tidyverse. I recommend being specific about like which packages you attach. But when you're doing some EDA with your data, just loading in tidyverse is really, really nice and convenient because it suddenly makes like all of those packages, the functions available for use. So in this example, first I create a tibble with one column and its n sample, and that's just going to have 3 rows, 3, 4, and 5. And then I use the mutate verb from the dplyr package, and in that I create these 2 new columns. One is called sampled states, and that's where I use the per package, and it has this function called map, where it allows you to map a function. It allows you to apply a function to a set of values, and in this case, what I'm doing is I am sampling like states I'm sampling states based on number of times to sample. So when it's running through the values in the and sample column, it's going to call sample. It's going to call a sample with sampling 3 states. Then it's going to sample 4 states, and then it's going to sample 5 states. Well, specifically state abbreviations. And then what's cool is that in mutate, you can, after you've defined a column, you can then use it immediately after. So I have the concat states column, and I'm specifically using the map character function of per. The underscore blah 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 allows you to specify what the output value is going to be. So if you have some issues in terms of like the type of stuff that a function is returning, you're going to get errors there, and you're going to be able to catch them. This is like we're slowly getting towards like strict typing in R, and it's really cool because it allows you to anticipate your outputs. So what I'm doing there is I'm going to apply the paste function to the elements in sample states, and I'm going to collapse them using the comma space separator. So when you look at the final output, you have the n sample, which is 3, 4, and 5, and then we have sampled states, which is a list of vectors, character vectors specifically, one with 3 elements. So those are the 3 state abbreviations that were sampled. Then we have 4 state abbreviations that were sampled, and then 5. And then we've created a new column that was a concatenation of those. So right there, I think there's a lot going on, but I think it really illustrates like the amount of complexity that you can achieve in just like a few lines of tidyverse code. Any questions so far? Okay. All right. So then we're going to take that tibble that we just created, and we're going to pull out the sample states column. So this is the column that had the lists. And then we're going to apply the tibble function to each one of those, and that's going to basically like output like for each row in that column is going to output a tibble, aka a data frame with the state, and then we're going to underscore DFR means that the output we're expecting is a data frame, and then the R means that we're going to do row-wise binding. So we're going to create like a data frame that is, R-bound. That is the R-bind version of all of those. And then we're going to group by state, and we're going to run tally. And tally will just create this new column called an that contains like a count of how many times we've observed that particular value. So if we go back, we see that Georgia, for example, appears twice in the concatenated states. And yeah, we see it, have a count of 2 over here. And then we can use the spread verb from tidier to go from a tall data set to a wide data set. So we're going to say, okay, basically create a column for each state, and then use n as the value in that column. So we get those. And that's it for TidyVerse. Thank you for coming to my TED Talk. I realize that there's a lot going on here, so hopefully this was like a nice quick dive into the deep end of the TidyVerse, and there's like so much I haven't even covered yet, but hopefully this maybe piqued some interest. All right, so probabilistic programming languages, PPLs. So when I was talking about Bayesian modeling as like you're modeling the data generation process, and probabilistic programming languages allow you to specify your probabilistic, your Bayesian model using a programming language. So these are languages where like random variables from probability theory and statistics are like first-class citizens. So you have variables that have distributions assigned to them, and then once you specify your model, you use algorithms like Markov chain Monte Carlo and variational inference to draw samples from the posterior. What you're doing there is instead of like analytically figuring out what the posterior is, which is really, 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 really hard, if not impossible in most cases, because in order to like analytically figure out what the posterior should look like, you really should be using like conjugate priors, and these are like priors that when combined with likelihood yield posteriors that have like the same form. But in real life, you're not really encountering a lot of that. And so you have to rely on these like approximation techniques like MCMC in order to approximate the distribution of your posterior by sampling from it in an algorithmic way. And these samples that you get, they don't converge to a value. Like it's not like running an optimization algorithm that converges to a specific value. You're running this algorithm where the output converges to a distribution, to a probability distribution. And that's a big if, like if it converges. So if you're an R user, you may have encountered like bugs and jags at some point. So these are like WinBugs was for a very, very, very long time, for many decades, like the go-to PPL when doing like Bayesian statistics. And then and then I think for the most part it was replaced with JAGs, and JAGs. I think last release was like a couple of years ago, so still pretty recently maintained. But it has been, I think, superseded by Stan. So Stan takes a lot of inspiration from JAGs, and then does a lot of like really smart things. It has some limitations. So JAGs allows you to have discrete random variables. Specifically, sorry, you can have discrete random variables in Stan, but you can't have like latent discrete random variables in Stan, which is to say you can't have unobserved parameters that are discrete because of the like the underlying like mathematics that Stan uses. You can only have continuous latent variables, and you have to do some like funky stuff in order to have latent in order to have discrete latent variables. But and then in JAGs, because it's using Gibbs sampling as opposed to Hamiltonian Monte Carlo, it allows you to have discrete latent variables. And then there's Grada, which is a very recent development. It's powered by TensorFlow and TensorFlow probability, and it's actually what I'm going to be using to like give a demonstration of probabilistic programming in R. Because what's really cool is that it turns R into a PPL. Like it allows you to have these random variables that are first-class citizens in the world of R. If you are a Python user, PyMC3 is like the gold standard when it comes to doing Bayesian statistics. It's very popular. It's like still maintained. They're currently doing PyMC4, which is, and they're transitioning to like TensorFlow and TensorFlow probability as the backend. But like PyMC3 has a lot of examples and tutorials out there. So if you are a Python user, PyMC3 is definitely the one to go to. So for like learning how to do probabilistic programming. Then there's Edward 2, which is included in TensorFlow probability, and there's Pyro, and this one's created by Uber, I think, and uses PyTorch as the backend. And then Pomegranate, which is similar to like Grada in terms of like a very recent development that's still kind of in early stages. So the API is developing, isn't still in development. So if you're going into Bayesian modeling for the first time, I might recommend, like if you're an R user, I might recommend JAGs and Stan. And then if you're a Python user, PyMC3 for sure. And then pretty recently, there's also InferNet, which is Microsoft's, Microsoft Research developed this thing. And I think InferNet is used to do like skill ranking on like Xbox Live. I think they do, yeah, they use this thing called TrueSkill. They have several papers out on it where they use Bayesian modeling to like infer player skill in order to do matchmaking. So it's really cool. And that one's designed to handle like a lot of data and like really complicated models. Okay, so a quick example of probabilistic programming. Let's say that we want to estimate a coin's hidden probability of coming up heads. So in R, we load up Greta. So on the back end, because this uses TensorFlow probability, it's using like RStudio's Reticulate package in order to connect to the Python library there. So if you're having troubles like installing Reticulate and installing the TensorFlow R package, you're not going to have a lot of luck installing Greta or using it. But in this example, everything's fine and dandy. So we're flipping a coin with probability of 80%. We're flipping it 10 times. So first we define this parameter, this unobserved parameter theta, and we're going to say that a priori it follows this beta distribution, and on the next slide I'll show like y specifically 3,3. So in Greta, first we say, okay, y is going to be this Greta data array from X, and then we assign a distribution of binomial. So that's like specifying the likelihood part, and then we create this model. If we plot M, it produces this directed acyclic graph of how the different parameters and hyperparameters play into our model. So we have shape 1, shape 2 going into beta, and then beta, that's the distribution for theta, and theta is the probability parameter for the binomial distribution that is associated with y. How did we get beta 3,3 as the prior distribution for theta? I used my package, which is it's called tinydancer, and I really like the name, and I mostly wanted to create a package called tinydancer because I thought it was hilarious, and it just kind of magically worked out that that was a really good name for this particular package. Thank you. Tanya says best package name. Yeah, so tinydancer is a package that enables an RStudio add-in. So RStudio add-ins are like these plugins that you can install, and then they're these like small shiny apps that run inside of RStudio, and they have like, you can just make a shiny app that does a very, very small specific thing, and you can just have a bunch of them. So people have made ones where you can like pick colors or edit ggplot2 objects, or do like citations. There's a whole bunch. And if you look up like RStudio add-ins, you can probably find an index of some really cool tools. So this one adds 2 add-ins called univariate continuous distributions and univariate discrete distributions. And these, one, I think are a really cool teaching tool because it allows students to really like play around with the parameters of a variety of different distributions and see how the choices of those parameters affect the shape of the distribution. For a few distributions, I offer like what's called a classic parameterization, and then a more intuitive parameterization. And then when you finish running it, it outputs the chosen values. So in this particular case, I'm running the beta distribution, and then that's what it looks like with 3.3 as the choices of shape 1 and shape 2. So what that's saying is I'm placing most of my probability like around the 0.5 value, which is to say I don't have like a lot of like intuition to offer, a lot of prior opinion that that the value for theta, which is our, the probability of getting heads on the coin, that it's towards 1 or towards 0. I'm very much saying like that the most likely value is like around 0.5, and the values on the extremes like 0.0 and 1.0 are very, very unlikely in comparison. So that's what's really cool about like Bayesian modeling and specifying prior distributions, is that you're formalizing your opinions, your intuitions. So once we have that model, we use MCMC to do our inference, and then we can visualize the posterior distribution by looking at the density, and so that's what we get. As you recall, the like true value was 0.8. So based on like these 10 coin flips, the posterior moves from being centered at 0. Like the distribution for theta moves from being centered at 0.5, which was our prior. After observing the data, it moves, to the right, closer to like the true value. Cool. And then inside of Broom, there's this package. There's this function called TidyMCMC, and then it works with objects that are it works with samples that are produced by packages like Grada, RJAGs, and RStan, and it allows you to look at the estimate and the confidence interval. Although in Bayesian statistics we call them credible intervals, and they actually do have like the interpretation of the true value has a certain probability of being inside this interval. We can also get the highest 95 posterior density interval, which is slightly different than like using quantiles to get your credible intervals. And if you have questions about that, I'll happily answer them like after the fact. Okay, so let's do a quick study, or case study. Going through a wet Russian right now. So let's say we
as a Russian. Huh? That's fitting as a Russian.
Yes, it is a very cannibalistic drink, isn't it?
Just had to get my 2 cents in, and also that tinydancer package name got me. Okay. Good.
So suppose that we are managing a store and we get 300 customers a day on average, and then we run this advertisement campaign for 30 days, and the intention is to like increase business, and it takes like, it doesn't have an immediate effect, takes some time, but once it does, there is like that increase in number of customers that we get per day. And then after we're done with the advertisement campaign, there is like that maybe there is a new normal, so to speak. So we've gone from one certain rate of customers per day to this temporary rate of customers per day during the advertisement campaign, and then a third rate of customers per day after the campaign. So we want to estimate like those short-term and long-term effects of the ad. I do have like this like fake report that you can check out, both like the PDF version that's produced using that template that I talked about earlier, as well as the R Markdown source code if you want to see like everything that's going on inside. So let's analyze this using Bayesian modeling. So first of all, I do want to show this example of like how you might format a table inside of R. So this uses that cable extra package. So first, oh wow, I guess sorry, okay. So question, what fit were you displaying on the previous graph? Okay, this isn't, so this is not a fit. Here I'm actually displaying like the true, like the underlying rate. So the blue is the actual truth that was used in the simulation, and then the black are the simulated number of customers per day, according to like an underlying true rate. So first of all, this code is now deprecated because data frame is now deprecated in the new version of dplyr. Now it's tibbles or not. So here I create this, for all intents and purposes, a tibble, and I'm having this column parameter. So you'll see that I'm using LaTeX inside like the values for the parameter column, and then I am also specifying this column called value, which is where I specify the true values that I used in the simulation. So let me actually stop sharing my screen and then share RStudio real quick. Okay. There we go. So this is the report. I should probably do this, do that. Increase the text size a bit. So this is the R Markdown report. This actually has the simulation code. So these are these like simulation parameters that I'm defining inside the R code. And then that's what I end up using in the simulation code. And when I I'll go back to this. Hopefully that didn't mess up with the recording. I apologize profusely if it did. I'm sorry.
Looks great.
Okay, cool. Yeah, so here, I specified like the value column, and I have the true values that I use for the simulation. And then I run it through the cable function from knitr, KNITR package. And I specifically say escape equals false. So that's the thing that allows me to interpret like this LaTeX correctly. And then from the cable extra, I have cable styling, which in this particular case, I'm just using it to specify hold position. So this is to make sure that the table, when I knit, aka render the R Markdown source document, the table it shows up more or less where I have that code chunk, as opposed to being put like on a new page. And it also has this function called group rows, which actually conflicts with the new release of dplyr. So that's going to be interesting to see how that development goes. But as of before the new version of dplyr, this group rows function allows you to specify this index, and this is, you say, okay, my first 3 rows are going to be called rates unknown, and then the next 5 rows, I'm going to group them into a group called other parameters. And so you end up with this nice little table where you've grouped up your rows, things are nicely formatted using LaTeX, and it looks pretty. Okay. Now, model specification in Stan. So this is the probabilistic programming language that I'll be focusing on in this talk. Sorry if that's confusing with me using Greta earlier. I just thought it was like much easier to show probabilistic programming languages using Greta. So in Stan, you have three core blocks. You have your data block, which is where you're specifying like all your inputs, and then you have your parameters block where you're specifying your your unknown parameters. These are what you want to infer using your model. So in the model block, that's where you're specifying your priors. That's where you're specifying your likelihoods. So in this case, if you look at the simulation code in the R Markdown source, it actually looks pretty close to like the model specification that I have going on here. So this takes a lot of like Stan was developed by statisticians who use R and who use C++, and so it takes a lot of ideas and inspirations from those. Here we're saying this rate parameter lambda, which we specify as being three parameters, an array of three different lambdas, and all three of them followed the normal distribution centered at 300, and for each observation in our total of n observations, if I is greater than t1, so this is like the time at which we started our ad campaign. We say if it's after the time we started our first after the time we started our ad campaign, but then before we finished it, then our observed data is coming from a Poisson distribution with this particular lambda rate, and then otherwise, so this is after campaign started, and then after it finished, it's coming from Poisson distribution with this rate, and then if it's before we started our campaign, then it's coming from Poisson distribution with the first rate. So then when we actually sample, this is actually like the simple model. This doesn't take into consideration that after we started our campaign, there was like this gradual transition to the new rate. This is a model of instant impact. So we specify that, and then in the GitHub repository, you can actually look at the second model, which is like the model of gradual impact, or this gradual transition to the new rate. So those are the two models that I'll be comparing. So in RStan, I'm specifying the models as a list and using the STEM model to compile the specification that I just showed you into C++ code that it's then compiled into an executable. And so when you are using sampling in order to do your inference, that's what's actually run. So probabilistic programming languages are like all about you specify your model as a program, and then it's run, whether it's like compiled or what, it's run, and then it outputs these posterior samples. So the reason that I specify these two models inside of a list is because using TidyVerse, I can actually like apply a bunch of different functions to the elements of this list, using things like per and others, and then get back a list of things that I can then do further work with. So it facilitates, like TidyVerse facilitates working with large amounts of data that's combined in some way. So in this case, I do have these two models that then I use like that same map function. from per, where I apply the sampling function to each element in the models list using this data, and then using some, like, specifying additional parameters to pass on to the sampling function. Now, I do make a note that, yeah, if we had the two models use different data blocks, we could then provide different data objects, put them into a list of the same length as the model's object, and then use map2 to go through both of those in parallel. So for each element of models, we then use the corresponding element of data, and then combine those in the sampling function. So it's really cool and it's really versatile. So once we do that, this is a function, a helper function that I created to basically create this like table. So the highlighted part is what's created using this function. So it takes the posterior draws, and then you'll see how this how I use this and like the overall process on the next slide. So first it takes the draws. So it assumes that it's working with draws from just a single model, and then it so it takes draws, and then it applies the TidyMC MC function and extracts the lambda parameters, and also generates these confidence intervals, or credible intervals, I should say. Then it applies the rename verb, it applies the mutate verb, so it changes the est column to be this combination of the estimate as well as the credible interval, and then we selected, so select allows you to just like pick certain columns that you want to get, that you want to keep, and we use that spread function from earlier, and then we return this extracted CI. So each of these rows in this table above was created by applying the extract CI function. And yeah, we see it here. So extracted CI. So we take the draws, and we apply the extract CI function, and we create this new column called model that has the identifier. So bridge sampling is the package that I use to compare the different models. And the way it works, it like knows how to, like, it specifically knows how to work with stan fit models. And there's like this whole paper that just describes like the theory behind it, but basically it calculates the log marginal likelihood, and then you can use that to estimate the posterior probability of your model given the observed data. So that's like the posterior probabilities data frame that I have there. So I have model, where, yeah, that's the identifier for the model, and then the post prob, that's the posterior probability, and I use the map double function from per to apply this log ML function, which extracts the log marginal likelihood from the bridge samples object over here in the top. Sorry, there's like a lot going on here, and hopefully some of it makes sense. And then if you do have a priori, certain intuition about which model is more likely than the other, then you can specify that in a prior probability argument. So once you do this, once you extract the log marginal likelihoods for the models, and then get the posterior probabilities, like, what do you do with it? You can do this. So This is that table that we saw from earlier. So we have these two tables. We have the posterior probabilities table that was generated from like applying the posterior probability function from the bridge samples, for the bridge sampling package. And then we joined that with the extracted credible intervals tibble. We use the model identifier as the key by which we're joining. And then we change what our posterior probability column looks like by applying this printf function. And then we also change how the model column, like that identifier column, looks by making it look fancy. And then we pass it on to the cable function. And we we specify escape equals false. That's the thing that lets us use LaTeX. And then in that same function, we're also specifying column names using LaTeX. So we want to show that, okay, this column is for like after the model identifier column, after the posterior probability of the model given data column. Then we have the lambda1 column, lambda2 column, lambda3 column. And then in parentheses, we also want to include like the true values that we used in the simulation as a reference. And we also want to group those columns together under a single column called estimate, and with parentheses, 95% credible interval. So that's what we use to do. That's what we use cable styling and add header above for. So all of that together is what creates this, what I think really nice looking table. Any questions so far? He asks with anticipation of complicated questions that he's not going to be able to answer. No? Okay. Inline Bayes factor. Okay, so Bayes factor is what you use to compare models. So Bayes factor allows you to, compare like the likelihood of one model relative to the likelihood of a different model, and then there's some interpretations that are out there. So if you get a Bayes factor that's between this value and this value, then you can interpret that as being weak support for model 1 over model 2. And then if you get like a Bayes factor between this value and this other model, then you can interpret that as like extremely, extremely strong support for model 1 over model 2. And then bridge sampling package that we used earlier to compute the log marginal likelihoods and then the posterior probabilities of the models, that includes a Bayes factor function that you can use to compare one model to another. So I include this particular slide to show how in this report, because it's R markdown, you can, well, first of all, you can use the markdown formatting, but then also you can cite your sources and references in line. So in the report, I have a corresponding like BibTeX file that has citations. In the WMF par package, which contains that that reporting template that I was talking about, I actually included this function to generate a BibTeX file. So these are like BibTeX entries based on a list of R packages that you provided. So because I firmly believe in citing like open source software that you use, like because that work shouldn't go like uncredited, I built in this function that makes it really easy. you just, inside of your R Markdown like header specification, you just say like, okay, these are the packages that that I've used in the creation of this report, and then it takes those and then combines them with the packages that that like the template itself uses, and it outputs a BibTeX file that has like all the appropriate citations. So here, yeah, I use LaTeX, I use the citation. I also use R inline. So R Markdown is really cool because you can have this paragraph where you're actually including R code inside of it. So instead of, you know, running your R code and then getting some results and then changing some stuff and trying to remember like, oh, where did I use those results in my document, you can actually have those results be dynamically included in the text itself, and so you never have to worry about making sure that your stuff is up to date. It just is. So that's another thing that's really cool. With the presentation of results, so this looks slightly similar to what I showed earlier when I had that table of the parameters and the true values. Only in this case, first we're specifically extracting the model 2's draws from the draws object, applying tidy MCMC with these parameters, or arguments I should say, and then we're formatting them in a nice way, and then we are applying this cable function with all this stuff. Oh, geez. With all the stuff and applying the cable styling. So in this case, because we want the rows to like have this like alternating background color thing, in order for them to be more like easily differentiable to the human eye, we have this striped option that we're passing it. And then, as before, we're doing the group rows, and we get this like nice table where we have the posterior differences. So in the model specification, let me actually jump to that real quick, because I think it'll be useful to see. So in model 2 spec, we have that data object, and in this particular case, D I think is the, if I remember correctly, it was the length, the length of time before, like, of the gradual transition before we get to like a stable rate. And then we have this slope parameter, and we specify this new model that takes into consideration that gradual change from one rate to another. But then we have this new block, which I didn't talk about before, but it's called generated quantities. And this block is really cool because it allows you to specify these new parameters that are like functions of the parameters that you're inferring. And so if you want to like answer specific questions about, you know, how different, like the ratios of your parameters, or like the differences in this particular case, or anything else, you can put those into the generated quantities block, and then you would have distributions, you would have these draws for those things that you're interested in, for, you know, for the differences, for the ratios, and it takes care of it for you, so you can answer, you know, probabilistic questions like, what's the probability that, you know, my ratio, that like the ratio between these between like average 1 and average 2 is greater than 1.0, or what's the probability that it's between this value and that value. So I think that part is really cool, that you can have these generated quantities, and then you can also do posterior predictive stuff. Like you can have you can generate observations using random number generations, and that's not a can of worms that I want to open right now, but just want to say that it is there, and it's really cool. Okay, so back to the slide deck. We're almost done here. Oh, yeah. Oh, yeah. So because the base factor for Model 1 compared to Model 2 is basically 0, there's no evidence for choosing Model 1 over Model 2. So Model 1 was the simpler. So this was a question from Dan. I think somewhere you picked Model 2 over Model 1. Yeah, so Model 1 was the simple change point model, and then Model 2 was the one with the gradual change. And because that one is closer to the actual like data generating process, the base factor ends up showing that there is much more evidence, much more support for Model 2 over Model 1. Yeah, so slides created with R Markdown and Sharingan, those are really cool packages. Source code is available. That's my contact information. Thank you all very much for listening to me talk a whole bunch about my workflow for doing Bayesian statistics in R.
Awesome. Thank you so much, Bearloga, Mikhail. Nate came in with a nice dad joke saying he's a stan of our stan. Thanks for that contribution, Nate. And yeah, we've had some good questions. I'll let everyone else chime in too, and feel free to come off and you can just talk if you want, or you can chat it, whatever you're comfortable with. But one thing that you taught me tonight, I had no idea you could make little add-ins like that for our studio. That's ridiculous.
Yeah.
It's like a mini Shiny app.
Yeah, like I mean, it is underneath it all. It is your creating this mini Shiny app, and it uses a package called Mini UI. But yeah, what's really cool is that if you find yourself doing a particular thing like over and over, and you just wish there was like some like shortcut you could use, or some easier way to do it, then you can totally just make an RStudio add-in, and you can have your own package where you just have a collection of add-ins that you've created for yourself. If you just find yourself just fucking struggling to make like markdown tables,
yes.
then you can totally have an add-in where it's showing you like a table, and then you can add rows, and you can input values, and then when you click done, it just spits out the markdown table with that stuff. So it's very versatile, and the limit is your imagination.
Yeah, it's crazy. I was looking at the code because I was seeing how easy it is, and it looks like it's pretty straightforward, and you just kind of add this viewer, like pane viewer, and then run gadget.
Yep.
Wow.
Yeah,
Okay,
and there's there is a GitHub repository out there somewhere that has like I remember seeing it has an index of a bunch of add-ins that people have created, and so you can check out that and see if there's anything useful there for you.
Yeah. And I don't want to monopolize. If anyone else has any other questions, I'll just keep talking. Oh, did someone just come off mute?
This is Dan. Thank you for the great presentation.
Oh, you're welcome.
I have a question, and it may be beyond the scope here, but I was wondering if you thought that there would be an application with these Bayesian statistics to try to separate two groups, just imagine two groups just on one dimension that we think are different, and we're trying to establish the most appropriate threshold for decision making for future. I'm wondering about how that could be formulated in a Bayesian approach, if that's something that you think would be useful.
That,
I mean, as opposed to maybe just building like empirical probability distribution functions and splitting the difference between them or something like that.
Sure. I think so. If I understand your question correctly, you're basically talking about clustering observations. Is that correct?
Yeah, I guess it would be kind of a univariate clustering, and then essentially identifying a threshold to separate them, so future cases, would be more likely assigned to one case or another.
Yeah. Think something called model-based clustering basically does that. Like it's saying that your observations are coming from like a mixture of Gaussian distributions, and you have let's say one distribution for one group and then another distribution for another group. As far as thresholds, let's follow up offline.
Yeah, right. Or I can also look into that. The model-based clustering is that a Bayesian application or not necessarily? I guess in that case then.
So yes, I think like the theory itself is Bayesian, specifically, but it like the model-based clustering that's available as like a software library. It doesn't use like probabilistic programming languages, but I think the underlying theory is Bayesian.
Okay, excellent. Well, I appreciate that. That's a great lead to follow up on. Thank you.
Yeah, you're welcome.
Cool. Any other questions? We got someone from Australia, I think. Steve. He'll be checking out the repo. Thanks for the great presentation. One last question for me, Mikhail. I started out my career working in biotech and doing some crazy Bayesian stuff, and I still feel like I don't know it well enough, and I learn something new about it all the time. Judea-Pearl's causality was like our Bible there. How easy do you think it is to, or not, to evangelize and like spread this stuff, like for example at your company, or just I find it difficult to explain sometimes to people that don't have a PhD in like math or statistics. Like, what do you recommend for that kind of issue?
What do I recommend for that kind of issue?
Just like it, spreading the good word of Bayesian stuff, or when you run into problems where it's tough to explain, right? Like I always go back to like the sprinkler, rain, grass example to like explain causality. I know causality might be taking this a little bit off topic.
No, yeah, I mean, yeah, like if you're if you're trying to like evangelize like Bayes theorem as a thing, and then using like Bayesian networks and causal graphs there, I think tailoring the actual like example to the domain goes quite a long way. And I haven't had to do this. Well, I mean, okay, so I actually recently did it at the foundation, but the example that I actually want to give is when I was explaining Bayesian network, because I was so excited about like learning Bayesian networks over the holiday break. I was explaining them to my wife, who's an educator, specifically like English teacher, and so does not have like a very strong mathematical background. And I like found this app on iOS that lets you define like very simplistic, like these are like Bayesian networks with nodes that are just binary random variables, and then you can also do your like conditional probability tables there, but you specify your like Bayesian network inside the app, and then you can you can specify which states are observed and what the observed state is, and then infer the probabilities of the unobserved ones. And so I ended up just like coming up with this example of like a student who took an exam, and then whether they passed or failed the exam, and then for the parent nodes, I use like whether the student cheated or not, whether the student studied or not, and then for the parent nodes there is like whether the student is a good student or not. So like just tailoring the example to like your audience was super huge, because she got it, man.
That's awesome. Yeah, you should, if you could share that app or like post in the Slack channel, I think that would be awesome. I'd love to check it out.
Yeah, it's called Embase, I think.
Embase, okay.
Yeah, on iOS, it's free.
Cool, sweet. Yeah. Well, I think that's probably it. No one's typed a question in chat, and this was awesome. Thank you so much for doing this, and we're trying to do these, I think maybe once a quarter, maybe twice a year. But I will be posting the recording when? Next week? Next week. So thank you, Mikhail, Bear Loga, Papa Dank. You have a bunch of aliases.
Papa Dank in the house. Thank you, Tanya.
Thank you for dropping knowledge on Bayesian modeling, and yeah, we'll see everyone in Slack, and we'll post it there soon.
Thank you.
All right. Bye, everyone.
Bye.